Geometry Common Core, the June 2016 Regents exam, starting on number 28. Find the value of r that will make the equation sine 73 equals cosine true when r is between 0 and 90 degrees. Explain your answer. So this has to do with a concept called cofunctions. And it has to do with when is sine equal to cosine? Well, it has to do with the fact that we know that sine is opposite over hypotenuse and cosine is adjacent over hypotenuse. Well, when you're talking about the two different angles, like if I were to call this angle A and angle B, angle C is our right angle here, the side that is opposite A, like this side for example, BC, like in this case, sine of angle A is BC over the hypotenuse AB, right? BC over AB. Whatever this is over this is. Well, it also works out that cosine of not angle A, but cosine of angle B is also that same ratio. And the reason for this is because BC is opposite to angle A. It's across from angle A, but it's adjacent to angle B. So when you're working within a right triangle, the two acute angles, the sides that are opposite one of them is adjacent to the other one. So when you switch acute angles and switch functions, you end up having the same ratios. And so that's when sine and cosine are equal to each other, is when you're talking about these two complementary acute angles, because these two angles add to 90. Remember, the three of them is 180, but these two together are 90. So what we get is a concept that sine A equals cosine B when A plus B equals 90, when they're complements. Because when they're complements, that means we're talking about the acute pair of angles in a right triangle. And sine of one of them equals cosine of the other, because the side that's opposite one of them is adjacent to the other angle. So for sine of 73 to equal cosine of r, that just means that 73 plus whatever r is has to equal 90. Very simple algebra here. We learn that r equals 17 degrees, because together they must be 90. Now explain your answer. I mean, I kind of just said it, but what would you actually write down? I mean, there's a lot of things you could say that I think would receive credit here. If you mentioned the phrase cofunctions, I think would certainly be good, but you could say that angles 73 and 17 are the two acute angles in the same right triangle. Again, I want to just get rid of those stray marks there. So then, therefore, the side opposite angle 73, and that's what this was, got kind of erased, is also adjacent to angle 17. And I think that isn't, again, there's a lot of different ways where you could kind of phrase this, but I think that's a good way to do it. No, let me go back to, so as a consequence, you also see a couple of things here. Sometimes we also see that like sine of an angle equals cosine of 90 minus that angle. And this is really kind of the same thing. That 73, well, sine of 73 is cosine 90 minus 73. So if you ever see this 90 minus theta or 90 minus x kind of thing, it's talking about the other acute angle within the right triangle. All right, now we can move on to 29. In the diagram below, circle 1 has a radius of 4, and circle 2 has a radius of 6.5. Angle A intercepts an arc length of pi, and angle B intercepts an arc length of 13 pi over 8. Dominic thinks that angles A and B have the same radian measure. Now, radian measure is really something that, honestly, in my opinion, belongs more in Algebra 2. than it does in geometry, and it really doesn't come up very often. If I can't really think of any other geometry. Maybe there's been one other exam in like the past 8 exams that mentions the word radian. But radian, again, I don't want to stress too much about this because like there's a good chance that you won't see this, but a radian is a way to measure arcs. Let me actually say measure arcs in radius lengths. And so what we mean by that is obviously this arc is, could they be the same degree measure? Sure. But if we were to measure them in like, centimeters or something like that, obviously this is a bigger circle. So this arc is going to be bigger than this arc in centimeters. But they might be the same radius measure, just like they might be the same degree measure. Because a radius measure is relative to the arc. Like, again, we'll find out exactly, but like, here's my radius of the circle, and here is the arc that we're talking about. I don't think they're equal, but let's say it's close to equal to 1. Like this arc length is pretty close to this radius length. Well, this radius is bigger, but this arc is also bigger. And again, I would say it's pretty close to 1. So there's a good chance that these have the same radian measure. As the circle gets bigger, the arc gets bigger. A simple way of saying this is arcs or angles have the same radian measure if they have the same degree measure, because it's the same thing. Like when you have a 45 degree angle, that the amount of arc, like 45 degrees of arc, that's really small if the circle is really small, but 45 degrees of arc will be really big if the circle is really big. So radians and degrees are very related. It's kind of a way of measuring degree measure, but relative to the radius length. So what we're going to do in this question is try to figure out, do these angles have the same degree measure? And if they do, then yes, they have the same radian measure. Now the way to do this is with our arc length formula. We have a formula that is, our x or theta over 360 times the circumference formula 2 pi r. Circumference formula is given to you, but the x or theta over 360 is not. But what we're saying for circle A is that it ends up equaling pi. So the angle we don't know. So I'm going to say A over 360 times, now 2 pi r with a radius of 4 is really 2 pi 4. That's going to be 8 pi. And we found out that this equals pi. The arc length is pi. So we're kind of doing arc length formula backwards to get angle measures. Well, we could get rid of the pi's, and you are going to be left with a 1 over here. It's not just nothing canceling out there. And so then I'm doing that times 360 divided by 8. Times 360 gets that on the other side, divided by 8. Inverse operations to move them over. And so we end up with angle A over here is 45 degrees. It's really 360 divided by 8 because the times 1 doesn't do anything. And how about for, let me erase this for some space. How about for circle B? Well, it's going to be B over 360 and times 2 pi r with this, double that is 13 pi. And we're saying that equals 13 pi over 8. Again, we could get rid of the pi on both sides. And I'm going to times 360. So let me actually do this over here. So B is going to be this 13 over 8 that was there. I'm going to do times 360 to move that to the other side and divide 13 to move that to the other side. You see, you can use your calculator here, but you can see that your 13s are going to cancel out. And again, it ends up as 360 divided by 8. So yes, again, angle B is 45 degrees. So explain why. What we could say here is simply, yes, both angles have the same degree measure Therefore, they have the same radian measure. All right, so that's that for arc lengths. Let's check out 30 and see if we want to try to do this. Yeah, I think we get 30 in and still make this about a 13-minute video. A ladder leans against the building. There's always ladders leaning against building in geometry class. So here is our building here, and you have a ladder leaning against the building. The top of the ladder touches the building 10 feet above the ground. The foot of the ladder is 4. So here's the foot of the bottom is 4 feet from the building. Find to the nearest degree the angle that the ladder makes with the level ground. So here's the ladder, here's the ground, here is the angle we're looking for. So we're talking trig, and we're working with, from our angle theta's perspective, this is opposite, this is adjacent. We're not using the hypotenuse, so that is the tangent function. Because remember, tangent is opposite over adjacent from SOHCAHTOA. But we're finding angle measures, so we don't do, a regular trig function would look like tangent theta equals opposite over adjacent. And then we would cross multiply, but that we don't do that when we're finding the theta. We only do that when we're finding one of the missing sides, like we have the angle and we're finding, like x is over here somewhere. When you're finding the angle, you got to do inverse trig. And the way you do inverse trig, first of all, a lot of students write this wrong. So inverse tangent, it's got a little -1 symbol, and then on the same side of the equal sign you put the ratio, and that equals theta. But I see a lot of students make the mistake of writing inverse tangent equals 10/4 or something like that. Like, that is wrong. There's not an equal sign between the inverse tangent and the ratio. They're on the same side. Like, by doing inverse, it allows these to switch sides, and this is what I type into my calculator to get angle theta and round to the nearest degree. So inverse tangent, 10/4. So turn on your calculators, clear it, just check my mode, make sure I'm on degree. And so the way we do inverse function is with the second key, then our trig buttons, inverse tangent. And so you kind of think of it as, second sine, second cos, second tangent. That's for finding angle measures. And we get 68.19, and we're rounding to the nearest degree, I believe it said. To the nearest degree, remember circle key words like that. That is exactly 68 degrees. Well, rounded it's exactly. And that's it. So that's 30. We will pick up on 31, which is a construction, in the next video. See ya.